Welcome to, this is Unit 4, but it's actually our Unit 3 now because we used to do it in the 4th unit, but we're doing it in the 3rd unit now. This is going to be circular motion. This is Chapter 9 notes. We're going to do Chapter 9, and we'll do a little bit out of 10 and 11 and a lot more out of 12, so it's not as much as you think it is. Alright, our first definition word is rotation. This is when something is spinning, when an object turns about an internal axis. So if I was going to stand in front of the class and spin in little circles and you put a line straight through my body, I would be spinning through my internal axis. Like the Earth spins around its internal axis once every 24 hours. Alright, an axis is a straight line around which rotation takes place. So like I was talking about, you can draw a straight line through the Earth and it spins around that axis. Straight line through me spins around my axis. You can also have an axis that you spin out of. Say like the Earth rotates or revolves around the Sun. You could put a line through the Sun and the Earth would rotate around that. And that's going to be our next vocabulary word. Now we have revolution. When an object turns about an external axis, like I was talking about. Like the Moon revolves around the Earth revolves around the Sun. So the Earth rotates around an internal axis and revolves around an external axis, which would be the Sun. We're going to have 3 types of speeds that we talk about, and each one is as important as the next. And some of them relate very well with each other, and some of them do not. So pay attention to these next 3 speeds that we're going to talk about in the next several slides. The first one I want to talk about is linear speed. Is the distance moved per unit of time. Have we talked about this before? We've talked about this a lot. This is going to be your velocity equals distance divided by time, or v equals d divided by t. We'll learn this in Chapter 2. It's come up again and again and again through this course, and it'll keep coming up. This is what we consider linear speed because it's in a straight line. And that's the first one of our speeds that we're going to talk about. Next we have what's known as tangential speed. The speed of something moving along a circular path, the direction or motion is always tangent to the circle. You see the circle we have here with the little lines coming off of it? Well, those little lines are kind of important. Those lines are the tangent lines. The tangent lines. So if there is something rotating around, it would go off in that straight line path. Think about it this way. Let me put the little marker here. Say that here in the middle is the Earth. That's our Earth. And out here is the Moon. I misspelled moon. Moon! Anyway, these straight line paths that it wants to take this direction, and if the Moon was here, it wants to go that direction. If the Moon was here, it wants to go this direction, or this direction. So if the Earth ever disappeared, it went away, the Moon would just take off in that tangent path. So this is the speed of something moving along a circular path. So it's going along the circular path because the Earth's gravity is pulling it down. The direction of the motion is always tangent to the circle. Those lines are tangent lines. That's something very important to remember. The lines coming off there are tangent to the circle. Alright, for this chapter, for circular motion, we use the terms linear and tangential motion interchangeably. Because we said that linear was a straight line and our tangent lines are a straight line. And we're going to be using those interchangeably in this chapter. So if you hear me say linear motion or linear and tangential motion, it's basically the straight line path carrying on from the side of the circle there. Alright, now the last one is rotational speed. This is the number of rotations per unit of time. We also call this angular speed. So this is the actual speed. This is not a straight line path. This is as you're spinning around in a circle, how many rotations you make per unit of time. So it's a distance, but it's a circular distance divided by time. So we had linear speed, tangential speed, and rotational speed. These are all 3 very important. So I hope we all know what this is. You can get on the horses and you can spin around and around and around. On these, you're going to have tangential speed and you're going to have rotational speed. Because as you're spinning around, you'll have rotational speed, but the further away from the center, you'll have greater tangential speed. And we'll talk more about that in the next few slides. Alright, if you look at this, we have a dot in the middle with a line coming out, and I've got the dots across the line, and it shows you the patterns that these spin around. Each bulb on the wire moves around the perimeter of the circle in the same amount of time. But the larger the radius of the circle is, the greater the speed. So as they move around, I don't know if any of you even know what a record player is, but a record player used to have 33 1/3 time. It would go around 33 1/3 times every minute. So it would go 33 1/3 revolutions per minute. So each one of these dots, whether it's this one, or this one, or this one, or this one, would revolve 33 1/3 times every minute. But the further out you go, the greater your tangential speed will be. The greater your tangential speed. The tangential speed is the one that goes in the straight line path. So the rotational speed would be the same all the way out, but the tangential speed would get greater the further out you went. All right, tangential speed and rotational speed are related. For instance, say you're standing on a large record player. If you stand in the very center, you have 0 tangential speed, but you do have rotational speed, because in the very middle, you're just going to be sitting there spinning in a little circle. Let me draw a little circle here. So if you're in the very middle, you would just be spinning in a circle at that point. But the further out you went, now you're going to spin around the circle and have actual tangential speed. At this point here, no tangential speed. Here, tangential speed. Rotational speed here is equal to the rotational speed here. As you move away from the center, your tangential speed increases while your rotational speed stays the same. Move out twice as far from the center, and your tangential speed is twice as fast. So again, if I draw another circle here in the middle, I have rotational speed. I have no tangential speed. But I move out twice as far, I'll have twice as much tangential speed. My rotational speed, still the same. It does not change. I move out twice as far again, I will increase twice as much. So tangential speed increases as you move out from the center of the circle. Rotational speed is the same anywhere on the circle. When a row of skaters lock arms and swing around, the guy on the outside has the highest tangential speed. Do you remember doing this when you were in elementary school? You'd go to the skating rink and everybody'd lock arms. You'd start spinning around and around and around. Well, everybody in that line would have the same rotational speed, but the guy on the very end has the most tangential speed. If he lets go, he goes flying off in a straight line path, and he will have the fastest linear speed, that tangential speed, out of anyone. And the person in the very center, if they were doing it correctly, would be just spinning around in a circle and not moving. If everybody let go, he would still be spinning in that space in the middle. Alright, to summarize, all parts of a rotating body have the same rotational speed. Very, very, very important concept. The tangential speed depends on the rotational speed and the distance from the axis. The further out from the center you get, the greater the tangential speed. Key points right here. Now we're moving into centripetal force. Centripetal force is any force that causes an object to follow a circular path. So, a force that causes something to follow a circular path. Can you think of anything like that? Well, think of our planet and the moon. There is the force of Earth's gravity pulling on the moon, causing the moon to travel in a circular path around the Earth. That would be considered a centripetal force. Let me speak well. And in accord with Newton's second law of motion, an object which experiences an acceleration must also be experiencing a net force. And the direction of the net force is in the same direction as the acceleration. Remember Newton's second law, force is equal to mass times acceleration. We just tested over this. So basically what he's saying is what we're going to explain in the next couple slides. This kind of got cut off. It's kind of, what do you remember about moving at a constant speed in the circle? If you're moving at a constant speed in the circle, what do you know about this? Think about it yourself, and we're going to talk about it in a minute. Alright, as it's moving around the circle, the velocity will not be constant because why? It's changing direction. If it's changing direction, it's going to be accelerating. Unbalanced forces on the object, you have acceleration. That point towards the center. So you see what we have here is, let me turn this back on, you have your tangential velocity in a straight line path here, but you're being accelerated towards the center. Because think of this as the Earth, and these dots on the outside as the moon, it's being pulled inward. It's being pulled inward. So velocity is not constant. Why? Because the direction changes. So the object accelerates because of this. You have now an unbalanced force. Unbalanced forces cause acceleration. So for an object moving in a circle, there must be an inward force acting upon it in order to cause its inward acceleration. This is sometimes referred to as the centripetal force requirement. So I'm going to repeat that. So for an object moving in a circle, there must be an inward force acting upon it in order to cause its inward acceleration. It wants to move in a straight line. Everything wants to move in a straight line. The only reason something's going to move in a circle is a force is causing it to move in that circle. And we're going to do a lab with this either tomorrow or the next day. The slide kind of got mixed up too. Examples of centripetal force. As a car makes a turn, the force of friction acting upon the turned wheels of the car provide the centripetal force required for circular motion. So think about it. As the tires are moving across, you have centripetal force pulling in because you have the frictional force on the tires. If you start to pull too fast, if you go around a corner too fast, your car will spin out. But because we have friction on the tires, between the tire and the ground, you basically can go in that turn. You're turning your wheels, you're not continuing that straight motion because the force on your tires on the ground is causing you to pull across. As a bucket of water is tied to a string and spun in a circle, the force of tension acting upon the bucket provides the centripetal force required for the motion. Why? Because the bucket, as it's swinging around, the bucket wants to do this. But there's an acceleration down the line. This is the velocity. It wants to go that way, but you have acceleration. The tension. Tension's just another fancy way of saying force. Is accelerating it that way. That causes the circular motion. As the moon orbits the Earth, the force of the gravity acting upon the moon provides the centripetal force because we have the force of gravity pulling down. The moon wants to go in a straight line path this way, but the force of gravity going down makes it go in the circle around and around, so that it's accelerating around. Electrons revolving around the nucleus of an atom are held in orbits by an electrical force that is directed inward towards the nucleus. So if you think about, you have the nucleus and you have the electrons out here. The electrons are being pulled in. The electrons are being pulled in by these electrical forces. Electrical forces are pulling them in, so they're accelerating towards the center. Alright, this is the last side, and this is a key concept for this. Centripetal forces are caused by center-directed forces. Centripetal forces are always center-directed. Center-directed. Center-directed forces. Always. Center-directed. That's a key concept. Do not mix this centripetal up with centrifugal. Centrifugal is not really a force, and we're not going to cover it in this class. Centripetal is center-directed. Centrifugal is something that pushes outward, but it's not a real force. And this is covered in your book. So what I want you to do, you've taken these notes, I want you to also read Chapter 9. Read Chapter 9. We're not going to meet in class again. Remember, we don't have school on Monday. You don't have an assignment for Monday. So you're going to have these notes, and I'm going to give you a workbook to work on too. So I will see you in class next time.